Hi, everyone. Can you all see the whiteboard?
Yes.
Okay. What answers did you get for the first one? Okay, good. 36 is correct. Nidhi, can you explain?
Yeah, so I define the terms because it says buy one get one third off. So I define buy one as X and a third off is 2/3 X. So to get two balloons, you're spending 5/3 X. We know that we originally had enough money for 30X. So 30, if you so 5/3 times 18 is exactly 30. So we know that from that we can afford 18 of that deal. So 18 times 2 is 36.
Good. Yeah. So if we assume like initially the price was X, second one is 2/3 X. So basically now you're paying 5X over 3 for 2. So you know that you had to have 30X dollars initially. So we could just divide this by 5X over 3 and multiply by 2. If we simplify this, we get 60 times 3 over 5, which gives us 36. So you can also do this a little bit the same way, but you could assume instead of using a variable X, we could just say one balloon is $1. Assume that initially. So then the second balloon becomes 2/3 of a dollar. And you know, so you get two balloons for 5/3 dollars or $1.66. And then you can use the same thing. So you had to have $30 initially, divide by 1.66, multiply by 2. It gives you the same thing. You're doing exactly the same thing as this, but you can just think about it in terms of a dollar rather than a variable X here. Does this make sense? Any questions on this? Okay, let's go on to the second one. Okay, good. 62 is right. Ishan, can you explain?
Yeah, so if 25 the diagonal, that means it can also be the hypotenuse. So you have to find the Pythagorean triple where 25 is the greatest number, which then that can be 24 and 7. So we just have to see if 24 times 7 equals 168, and it does. So then you want to find the perimeter, so you can just do a 24 times 2 plus 7 times 2, which is just 48, plus 14, which is 62.
Okay, good. Yeah, so we know the diagonal is 25, and we want to find three values such that it satisfies the Pythagorean theorem and the area is 168. So if you know the Pythagorean triple of 7, 24, 25, you can see that 7 times 24 is 168. So then the perimeter would be 7 plus 24 plus 7 plus 24, which would be 62. So good. This is one way of doing it. Any other ideas for other ways of solving this? Nidhi, did you do it the same way or a different way?
Yeah, I use Pythagorean triples, but I have an idea, I guess, for another way.
Okay.
I didn't really think about it too much. Basically, if we know that it's 168, because in the first method, 168, for me at least, it was more of a checking because I knew the Pythagorean triples. So I wanted to make sure that was correct, and that checked out. But if I didn't know them, I think I would do 168 divided by 2, which is 84. So we know A plus B is going to be 84. And then we know the diagonal is 25, so it would be a right triangle. I'm not sure.
Okay. So yeah, let's take A and B as the sides. So now can you give me an equation for what these two relationships are telling me in terms of A and B?
Can you repeat that?
Yeah, so let's say the rectangle sides are A and B. So now we know the diagonal is 25 and the area is 168. So can you tell me what that would be in terms of an equation in terms of A and B?
A squared plus B squared equals 25.
Equals 25 what? Is it 25 or something else?
Square meters.
Yeah, 25 squared. And what's the other relation?
A plus B is 84.
Careful, it's the area of the rectangular parking lot, right?
Oh, A times B is 168.
AB is equal to what?
168 square meters.
Okay, so there's no square root here, right? So it's AB is equal to 168 and A squared plus B squared is equal to 25 squared. What do we want to solve for here?
A and B.
Well, A and B ideally, but what if we don't care of A and B particularly? What is really the answer that we're looking for?
The perimeter, so 2A plus 2B.
Sure. So we want to solve for 2A plus 2B. Or basically, we can just solve for A plus B, right? If we know A plus B, it's twice that. Okay, so any ideas of how do I take, I know what A squared plus B squared is. I know what AB is. I want to solve what 2A plus 2B is. How do I do this? Okay, before we get there, let's do one more simplification here. What is 25 squared?
625.
Can you repeat that?
625.
Okay, good. And is there an easy way to compute this? Or is there a trick for computing this square without actually multiplying out 25 times 25?
Well, how I do it is I know 4 25s is 100, so it goes in 6 times. So it would be 600, and then there's one more, so it's 625.
Okay, yeah, that works. There's actually a kind of a general trick. If you have something like x5 squared, so this is where x is some digit. So this is like 15, 25, 35, 45, so on. For any of these numbers, if you want to find the square, you take the first digit, multiply it by the number above it. So let's say 1, you take 1 times 2, and then it ends in 25. So for 15, it becomes what? So I take the number 1, multiplied by the 1 above it, it's 2, and put a 25 at the end. It becomes 225. So what happens with 2? 2 times 3, and then 25.
625.
625. Good. Yeah. So this trick you can use more generally as well. But this is useful to get the squares in this format, especially for any number ending in 5. But okay, so let's say we have these two squared. Okay, so let's go back to the original question. So we know what A squared plus B squared is. We know what AB is. We want to solve for A plus B. Any ideas on this? What if, instead of telling you I knew what A squared plus B squared and AB is, what if I told you what A squared plus 2AB plus B squared was? Do we know what that is?
$625 plus 168 times 2.
Okay, we know what, so okay, 625 plus 168 times 2, good. Okay, now, can I go from this to find what A plus B is? What is this A squared plus 2AB plus B squared in terms of A plus B?
A plus B whole squared.
Yes. Okay, so A plus B whole squared is 625 plus 168 times 2. What is the 625 times plus 168 times 2? What is that?
$961.
Correct. Yeah. So now what is the square root of 961?
$31.
31. So what would the answer be?
$62.
Good. So this is an algebraic way of doing it. And in this case, probably the Pythagorean triple way is faster. But the reason why I want you to see this method is because I can instead sub in any numbers here, such that this is not a Pythagorean triple. It give you random square roots here. We can make this more complicated. In this way, you can solve it with any numbers, right? Because if I know what a squared plus b squared is, I know what ab is, I know how to make this a squared plus 2ab plus b squared. I can take the square root of that, multiply by 2. And even if this is square roots involved in this, you can always find the perimeter from these two values, regardless of whether you can actually fit a Pythagorean triple to match these numbers. Does that make sense?
Yeah.
Okay, so the nice thing here is because knowing the diagonal and the area there's actually a nice relation here. You can essentially, you're squaring the diagonal, adding twice the area, and it's the square of the sum of two sides, right? So you could actually kind of get a formula here, combining the length of the diagonal and the area to find the perimeter, if you think about what the exact steps that you did here. Does this make sense? Okay, let's move on to the last one. Any ideas on this? Okay, so this is a harder question, but let's start off thinking about, is there any way of simplifying this? Like I'm thinking about the hundreds digit of 2011 to the power 2011. Can you tell me it's the same as something else?
Well, the last three digits would be the same if we do 11 to the power of 11. Or to the power of whatever. It's just 11
to the power of 2011.
Why? Good.
Because the first 2011, it doesn't have a hundreds digit, so it wouldn't really change anything if you take it out.
Yeah, that's good. I think maybe to kind of convince yourself of this, if you think about 2000 plus 11 to the power 2011, right? So if you think about how this is expanded, whenever there's a 2000 term in it, it won't have a hundreds digit, right? It'll be 3 ends and 3 zeros. So the only term that really matters is the term that only has 11s in it. So that's 11 to the power 2011. But yeah, so this is correct. With 2011 to the power 2011, we can kind of just think about the hundreds digit of 11 to the power 2011. Okay, so now any ideas for making this simpler? Can I do something like this again?
11 to the 11th power.
Why?
Because you can just do the same thing, 2000 plus 11 on the top one, and then just it's 11 to 11.
So you have to be careful. We can't actually, so when I think about this, right, this is kind of like expanding in like the binomial theorem, right? So this is a plus b instead of squared, this is a plus b to the power 2011, right? And I can think about, this is going to be a to the 2011 plus 2011, choose one, a to the 2010, b to the 1, so on, so on. Right, you can kind of imagine the Pascal's triangle kind of expansion of a plus b squared, a plus b cubed, and so on. Now, you can't actually do the same thing with something in the exponent. So we can't think about, so 11 to the 2000 will also have some hundreds digit, right? or some 10s digit or some 1s digit. So we can't actually necessarily split this unless we know an additional property here. But yeah, go ahead.
I think would 10 plus 1 in the numerator, or not numerator, in the base be possible 10 plus 1 to the power of 2011?
Good, yes. So let's do that instead. So the base is a better, we can do a split. So let's think about it as 10 plus 1 to the power 2011. This is similar to what we did the split initially, right? Okay, so let's think about how does this expand?
10 to the power 2011 plus 1 to the power 2011.
So those are two of the terms. There's a lot more terms.
And there's also 2 times 10, 2 times 10 times 1.
Close. So if we're thinking about it kind of in the Pascal's triangle, when you think of squares, cubes, and so on, what the general form becomes 2011. So let me write out Pascal's triangle for a bit. So it's like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So these become 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, and so on. So what this becomes is 2011 choose 1 times 10 to the power 2010, 1 to the 1, plus 2011 choose 2 times 10 to the 2009, 1 to squared, and so on. There's now 2011 such terms ending with 1 to the power 2011. So basically, if you think about as I multiply this out, right? Imagine that I repeat 10 plus 1 2011 times, right? So then each time when I multiply out, I'm picking one term from this one, from this either 10 or 1, I multiply by one term of 10 or 1 in the second one, times one of them in the third one, so on up to 2011 times, right? So in total, I'm picking some 10s and some 1s. A total of them should be 2011. So either it's 2010 10s and 1 1, or 2009 10s and 2 1s, or 2011 1 chosen 2011 times. So basically, it's think about each time I'm picking a 10 or a 1, and there's 2011 such terms. So one option is I just pick 10 every time, or I pick 1 every time, or I pick some combination of those in between. Okay, so if you haven't seen this before, let's just say this is the expansion of this. Now, what can I kind of throw away in this expansion? What doesn't affect my hundreds digit?
1 to the power of 2011.
Okay. That doesn't affect, I agree. What about on the other side? Let's start from 10 to the 2011, 10 to the 2010 times this, and so on. What do these affect the hundreds digit?
No.
Why not?
Because it would just keep adding a 0. So after,
okay.
Yeah.
So if we have 10 to the 2011, right? This is going to end in 2011 zeros. This is going to end in 2009 zeros, 2008 zeros, and so on. So what are the terms we really care about here? So if it has 10 to the power 3, it'll end in 3 zeros. So it has to have only 10 to the power 2, 10 to the power 1, or 10 to the power 0. So let's think about what these terms would be. So this would be 10 to the 10 squared times 1 to the power 2009. Would be 10 to the 1, sorry, 220, sorry, what did I say, 2009? 10, oh yeah, 2009, sorry, that's correct. 1 to the power 2010 times 10. And then there's also the 2011 choose 2 here. Plus 2011 choose 1 here. Plus 2011 choose 0 times 10 to the 0 to 1 to the 2011. Okay, we already said this 1 to the 2011 doesn't affect it. So it's finally just comes down to these two terms. So what is 2011 choose 1 times 10? What is this? So this should just be 2011 ending with a 0 because we're multiplying by 10. Okay, let's look at this term. What is 2011 choose 2 times, so this 1 to the 2009 is just 1. We can get rid of this part. So it just becomes 10 squared. So what is 2011 choose 2? So you have 2011 items and you want to choose 2. What is the formula for that? So you can do 2011 times 2010 divided by 2. Multiplied by 100. Okay, so if we're multiplying this by 100, we really only care about the last digit of this. What is the last digit of this?
5.
Good, why 5?
Because 1 times 0 is 0. 0 divided by 2 ends in 5 always.
Good, yeah, that's correct. Or we can even think about 2010 divided by 2 itself is 1005. So it's 2011 times 1005, right? So this ends in 1, this ends in 5. So this ends in 5 times 100. So this will end in 500, and this ends in 110. So what should the answer be?
6.
Good, 6. So it's 610 is the last 3 digits, so 6 is the hundredths digit. Okay, so this is actually one way of doing it. There is another method which is a little more tricky, so I won't go over it, but if you're interested, you can look up the Euler-Totient function. And I believe Euler-Totient theorem as well is related to this, and there's kind of a number theory way of doing it. It's actually not very difficult to do, but I think it's a little more trickier. But if you're interested, you can look this up. And there's actually another way which is easier to solve this, but I think requires a little more specialized knowledge of this function and theorem. Any questions on this?
No.
Okay. That's it for today's class then. We'll see you all next week.
Thank you.
Thank you.
Thank you.
Welcome, bye.